This morning. My name is Pippa Hudson, really pleased to be part of the event today to help you celebrate this 50th anniversary session. And hope you had a good break. For those who caught the Liberty Mindfulness session, I hope you're bringing all that good, positive, calm energy into the room for the speaker. Just a reminder, if you haven't checked it out yet, the ACET chess semi-final is happening outside as well, so do dip in and see what's going on there during the course of the morning. To those who are joining us via live stream, welcome to you as well. Thank you so much for tuning in for the first of our concurrent sessions this morning. This one focused on short-term insurance, and with me as co-host, great pleasure to welcome Katlego Tlaba. Good to have you here.
Thank you, Piper. Good morning, everyone. Is everyone excited to be in the session? Those nods are not encouraging.
Not very loud.
All right, so I'll take your word for it for now, or maybe your nod for it. So as a quick reminder, we just ask that you ensure that you have your phones all on silent, and just to ensure we don't disturb our presenters during this session. And Piper, I'm very excited to have you here, and thank you for coming to our convention. I said to somebody online, or I put up a post online to say, you know what, because of your remarkable career in radio hosting, there's a risk that I come into this co-hosting an actuary and I leave as a radio host.
Are you saying you want to take my job? Katlego, it's really a pleasure to be here, and really nice to have somebody from the industry as co-host to help us navigate the questions particularly. So what we're going to do is, after we've heard from our speaker, we are going to allow roughly 15 minutes at the end of the talk for audience engagement. Please, we will have a roving microphone. If you'd like to ask a question, just raise a hand and we'll get that mic to you. Please do wait for the microphone to reach you. That's really important, not only so that everybody else in the room can hear you, but so that those who are following on live stream are able to listen to the question as well. And for those who are listening on live stream, just a reminder, you are also very welcome to engage with questions via the app, the WebEx app. For those who, anybody here hasn't yet downloaded the app, please do so. It's a really easy way to engage with the panelists today. So virtual attendees, you two are very welcome to post those questions, and we'll get through as many of them as we can at the end. Okay, so phones on silent, off we go. With great pleasure, let's call up our first speaker today. Deep neural networks, very important tool for use in actuarial tasks these days, and significant gains made in terms of accuracy compared to traditional methods. But what are the barriers to adopting them in insurance practice? And how can machine learning models be modified for practical use? Those are questions our presenter, Ronald Richman, is going to, I hope, answer for you over the course of the next 45 minutes. Ronald, great to have you with us. Morning, and welcome.
Thank you so much for that intro. And now, there we go. And one last request, can we get the screen on as well? Thank you, that's great. Okay, so just to kick off with a brief summary of what we're going to do in this talk, I'm going to start off by discussing some of the pros but also the cons of applying machine learning for actuarial work, and I'm going to do that in the context of a non-life pricing data set. What I'm then going to do is talk about how machine learning models can be interpreted, and with that idea in mind, build on this idea of this new machine learning model that we're presenting here called the ICEnet, which will show us how we're going to deal with some of the problems that we identify by just applying an off-the-shelf method. We'll look again at how this new model performs on this non-life pricing data set, and then obviously looking forward to discussing and getting your feedback on what we're showing. All the work in this is joint work with Professor Mario WUTHRICH from ETH Zurich, and you can find the paper online on arXiv. Sorry guys, this screen has just gone off again. If we could get it back on, that would be most appreciated. Okay, so I think we've run through the roadmap. Let's dive straight into the introduction. So maybe just setting the scene, I think where we are in the development of actuarial science and the actuarial profession is that traditionally, actuaries have been responsible for a lot of the numerical and statistical work in insurers, but today that scene has kind of expanded. You've got a lot of data scientists coming into the insurance industry, performing different tasks, and actuaries are finding themselves working alongside machine learning experts, data scientists, and all of those sorts of things to sorry, it's a little distracting with the screen going on and off, are working besides all these different professions in their day jobs. Actuarial science has always been the sort of hybrid discipline composed of finance, statistics, demography. And these days, I think what's happening is the discipline itself is being extended to bring in ideas from computer science and particularly machine learning and deep learning. And the Swiss Actuarial Association has gone so far as to say they think there's a new type of actuary out there. They call it the actuary of the fifth kind, and this is where actuaries practice actuarial data sets, merging all of the traditional knowledge and techniques that we have in our repertoire together with data science and machine learning. So if you look at the diagram or the Venn diagram on the right-hand part of the screen, I think today actuaries are somewhere along that journey towards incorporating data science and machine learning. But some of what I hope we're going to discuss in this talk is what are some of the pitfalls and how can you correct for them. So what is machine learning, in case people aren't familiar? So the machine learning definition that I always quote is, it's the study of algorithms that allow computer programs automatically to improve with experience. So what that means is you basically set up a certain algorithm. That algorithm can be something familiar like a GLM or something less familiar like a GBM or deep neural net. You show it lots of examples of what you wanted to learn, and this system starts to recognize patterns within the data to acquire knowledge. And what you can see on the right-hand part of the slide, this is an image from the Word VEC paper from Mikolov in 2013. What you can see from that diagram is that machine learning models applied in the right way actually capture some very interesting meaning or knowledge about the world when you apply it to large data sets. So this diagram, on the left-hand part, you see names of different countries, and on the right-hand part, you see names of capital cities. And you can see that in this low-dimensional view of what the machine learning model has learned, it's learned this almost intuitive mapping between countries and their capital cities and the way that they ordered. And that basically is one way of showing how this machine learning paradigm of picking an algorithm and throwing lots of data at that algorithm can actually derive a lot of knowledge about the world from your data sets. On this next slide, I just want to quickly talk about what are some of the tools that are now available in the actuarial toolkit. Starting from traditional machine learning, traditional actuarial models at the top, going to machine learning models, and then finally talking about deep learning models, which will be the focus of this talk. So traditionally, what's very interesting is actuaries have always enjoyed using regression models of some sort, generally linear regression models. And if you think about it, most of the work that we do in non-life can be expressed as some sort of GLM with an appropriate specification, and that's true of pricing, that's true of reserving, and you can see the attempt that we made to systematize that in the top left-hand block where we've got a formula, and the way to read that formula is an actuarial model consists of your input data, which is X, some sort of transformations of that input data. You might decide to log or square certain variables or group things together, and then you have this linear specification of a model. What that basically means is you have certain functions of your data. If you, in pricing, you might think about credit score, and you might want some sort of function that shows increasing claims frequency as your credit score decreases. And what you're going to try to do is calibrate the parameters of this model in order to give you good predictions. And this is the traditional way of looking at actuarial modeling that you cover when you study to become an actuary, but also when you get to the workplace and you start using the tools that are currently available. Where's the world going now? The world is now moving towards using machine learning models, particularly outside the actuarial field, but I think also within the actuarial field. And the main thing that machine learning models do for you is you no longer have to manually specify what is your model. You implicitly specify a model, and we have that with this symbol over here, after picking a certain class of algorithms. And some of the algorithms you might be familiar with might be decision trees or random forests or gradient boosted trees. And you effectively outsource the creation of the model and the selection of what exactly those relationships should look like. You outsource that to the machine learning algorithm and basically hope that you get a good predictive answer, and most of the time you do. And then finally, the last tool that's now available is deep learning. So deep learning, not only do you outsource the modeling of relationships in your data to the model, you also outsource the transformation of your data. So what do we mean by that? Imagine you've got some very high-dimensional and difficult to understand data coming from a telematics device. What you can do is feed that into an appropriate neural network. And as long as you've chosen the neural network in an appropriate manner, you can start to get very good predictions straight out of these models without doing a lot of work, say, deriving scores from your telematics data, which is one approach that's prevalent in the market. You choose the neural network and you allow the network to do the job for you. So these are the tools that are available. And let's summarize why should you care about AI and actuarial science. I think there's a couple of points to think about. Actuarial tools traditionally rely on a huge amount of human input. You need people to manually specify what features you want to derive from your data and the sorts of models you're going to use. Deep learning in particular, these types of models offer a good empirical solution to both of these modeling tasks. All you need to do is pick the right sort of deep neural network. It's going to learn an optimal representation of the data you feed it and give you really good predictions. So that's really great. But what are the potential costs? So the one potential cost is not really understanding or having control over the relationships learned by the network that you apply to your data. And what we're going to look at is what are some of the pitfalls that you might run into as you apply these models. Okay, let's get the clicker to work. So this is an example of some models that were fit to a paper that was released this year from Michael Mayer and his colleagues. And this paper was all about machine learning interpretability, focusing in particular on the SHAP method. I'm not going to talk about SHAP in this talk, but it's just a way of interpreting machine learning models. And basically, what they did is they fit 3 different models to the synthetic data set that had been generated. So you know what the ground truth is, and the ground truth is shown by the black line in each of these graphs. And what they've then gone and derived is an interpretability method called the partial dependence plot that we will talk about a little bit more as we go through this talk. And they've derived that both for the ground truth in black, a neural network model in red or pink, the light GBM gradient boosting package, that's in purple, and finally just fitting a GLM and hoping it throws out something useful, and that's in yellow. And they've done that for driver age on the left-hand part of the slide, and they've done that for the power of the vehicle on the right-hand part of the slide. I just want to point out something interesting. In this paper, the best performing model is the light GBM model. But let's look at what sort of relationship it's learned in the data. And what you can see is light GBM is relatively smooth and follows the truth quite closely. But at some of the older ages, you get this sort of spikiness. And that's probably evidence of the model not fitting particularly well at those older ages. Also, with vehicle power, you get this sort of horrible spikiness. I'm calling it horrible, and maybe I should justify that before I do, over the entire range of car power. And important to keep in mind that this is a relatively simple data set where you know the ground truth. And even in this particular instance, a gradient boosting model is giving you a relationship that looks like it suffers a little bit from lack of credibility. So traditionally, actuaries have always liked smooth and monotonic features wherever you can get them. And I think what you can see very clearly here is that, at least in this particular example, this isn't working. So tomorrow morning at 8 o'clock, I'll be talking with Kovlin Perumal on climate change modeling. And this is also an example of an individual conditional expectation plot. And we're going to talk a lot about what that means in the slides that follow, so don't get too worried. It just shows the relationship for an individual policyholder of the outcome of a machine learning model with a particular covariate. And the covariate that we've got over here is a measure of rainfall. And again, here's a partial dependency plot showing exactly the same relationship, but over the whole portfolio. And again, what you can see is what we would expect is as rain increases in a particular area, you should have a relatively smooth relationship that you learn with your machine learning model. But what you see is, in fact, you get these massive jumps, which are very hard to explain. Then you get these decreases, and it's all kind of spiky. And that's not exactly what you'd want to put into practice in a rating model. Policyholders will ask, hey, we had a little bit more rain, or if we just go back to the previous slide, or, for example, I got 1 year older, why is this really severe jump happening? And that's the sort of thing you don't want, practically speaking, but this is a pitfall of what you might actually get from naively picking a machine learning model and running it on your data and hoping you're going to get something that's credible. So one particular solution to this problem you might think of is, let's get rid of machine learning. Let's just stick to our GLMs. I don't think that's a good answer, because GLMs are very difficult to maintain, and the process of fitting them the way actuaries have traditionally done it in non-life insurance is very tedious in my view. Another option would be, can we fix this? And really what the rest of this talk about is, how do we fix these sorts of pitfalls that you might have if you're fitting a deep neural network? What we're going to use to illustrate this is this French motor third-party liability data set. This is available on the internet, and it basically, it's a pretty simple data set. You've got a couple of the things that you'd expect, like exposure, number of claims, claim severity, and a bunch of different covariates that you can use to price for. There's about 680,000 records, and what I did, and what we'll be working with, is this sort of split, a 90-10 split, and there's a frequency of about 7.3% on an annual basis. Well, I just want to show you some of the relationships in this data set. So let's start with exposure, which is in the bottom right-hand part of the slide. You can see some of the most important covariates are bonus malus, which is like our, what I guess you'd call a no-claim score in the South African market. Most people have got the best number of a bonus malus score of 50. Density, how dense the region is where the policyholder lives, a kind of a nice distribution across ages, with relatively fewer policyholders at younger ages and the oldest ages, similar for vehicle age, and then vehicle power. We don't have too many of the most powerful vehicles. And if you just look at the one-way analysis in the top left-hand part of the slide, what you can see is a lot of the relationships that you'd expect intuitively are in fact there. So you've got an increasing claims frequency as your bonus malus score gets worse, as it goes from 50 to 200. Your frequency also increases as density increases. Your young drivers are worse than at least your older or middle-aged drivers, and there's a lot of noise at the tail for driver age, a decreasing relationship for vehicle age, and then vehicle power, even on a one-way analysis, you can see is a little bit all over the show, which is kind of weird, and probably some sort of confounding going on there. So what you might be tempted to do is think about what sort of constraints you might want to apply to these variables. And what we'll see later is really what the ICEnet is how do you constrain your model to fit the relationships the way that you think they should be fit. So let's talk a little bit about machine learning interpretability. So on the one hand, by using machine learning models, you get much greater predictive accuracy far quicker than you can with traditional actuarial modeling. That's my conclusion. I don't know if, and I should say it's an opinion. I don't know if anyone in the audience perhaps disagrees with that. But another one of the problems is that machine learning models are opaque. So like we said in the introduction, you let the machine learning model specify all of the relationships for you, in your modeling. You don't actually do that yourself, so it can be a little bit hard to understand what relationships has your model learned. So this is why the field of post hoc model interpretability has developed. I should have drunk more coffee this morning, clearly. And this is methods to determine how exactly your model has captured the relationships between variables. There's a whole zoo of these sorts of techniques. We'll be talking about partial dependence plots, which are PDPs, and individual conditional expectations, which I'm just going to call ICEs. But there's also, I'm sure people know about Shapley additive explanations, or SHAP, or LIME, which is local interpretable model agnostic explanations. So we're only going to focus on those first two. Maybe just by show of hands in the audience, who's ever seen or applied some of these methods before? So I'm going to estimate about 30%, so that's great. And what basically the way that you apply these methods is, there's a very simple recipe. Step one is you fit a machine learning model exactly however you'd like to do it. This could also be a traditional actuarial GLM. You then modify the input data that you feed into this particular model in a specific way, and you do those modifications so as to isolate the effect of a single variable. And then what you basically do is you repeat this for all different combinations of the data, look at the outputs from the model with the modified inputs, and effectively you get a very good idea of how your model is performing. So let's talk about those first two, ICE plots and PDP plots. So the main idea of an ICE plot is actually very simple. All you do is you take your model, and what you want to test is how does your model output change as you vary one input variable. So you do this on a per policy basis or a per record basis. And as you vary the one input variable, the output that you get from the model is the marginal impact of making that change to your data. So let's just put it in similar terms to what we've been discussing to this point. Maybe you've got driver age in your non-life pricing model. Maybe you'll change the age from 50 to 51, 51 to 52, and you'll see how does the model output or the predicted frequency, or whatever it might be, change. And that's how you derive an ICE plot. So the ICE recipe is you fit a machine learning model, you modify the value of a single input variable to isolate the effect, and you repeat that for all the records in the data. And we'll obviously show an example of that very shortly. A partial dependence plot is the average of all of those ICE plots over your whole data set. And I'm not going to talk too much about how to interpret this from a causal perspective, but there's a nice reference there if anyone's interested in causal inference. So here's a first example of partial dependence plots. And what you can see is the same one-way analysis that we had on this data set in the top left-hand part of the slide. So just remember some of these relationships. And then on these graphs on the bottom, we've got partial dependence plots for these same variables. There's bonus malus, here's density, and there is driver age. And what you can see that in some case, the partial dependence plots are a little bit different from the empirical data. So let's isolate and look at driver age. What you can see over here is your partial dependence plots actually going in the opposite direction of your one-way. And the reason that it's doing that is what partial dependence plots do is try to isolate the effect of a single variable, whereas obviously your empirical or your one-way plots are influenced by different correlations that you may have in your data. So for example, in this particular data set, your youngest drivers haven't been around long enough to get a good bonus malus score. So as a result, their bonus malus scores will probably be at the starting value, similar to 100. And bonus malus captures that effect of driver age more than the driver age variable itself does in this particular data set. So that's the first example of partial dependence plots. As we said, the way to interpret this is, let's look at bonus malus. As your score gets worse, so too you will produce a higher prediction and a higher prediction of frequency. Let's have a look at what ICE plots look like. So here we have got, I think I selected 50 from a deep neural network fit to this French data set. The plot all the way on the left are your different individual conditional expectation plots. I've tried to just color them by which policyholder this is in this data set, and you can see that these are much more variable than the partial dependence plot, which we've got in the middle. You can see they are quite spiky, quite jagged, and they actually also, very interestingly, change direction. So some of them have got a decreasing risk profile with age, some of them have got an increasing risk profile with age. And again, if you think about it, let's say we have fit a deep neural network, or for that matter, any machine learning model to a pricing data set, and you're now going to deploy that in practice. If you don't carefully look at these ICE plots, you could have all of these sorts of weird features in your model, even if it turns out to be very accurate. And that's exactly what you don't want. You don't want to go to your broker or your policyholder and say, hey, we're suddenly increasing your premium now after it's been decreasing every year, because that's just what the model says. That's kind of a classic pitfall of the fact that you'd be using a black box for your rating. And really what the rest of this presentation is about is what is an automatic way of solving this problem. What I want to suggest is that when you think about the traditional process of non-life pricing, and this might be with reference to a specific tool that I'm sure many people in the room know of, what you often do is you fit a GLM, and the equation over here is just a GLM on the scale of the link function. And you can see all your GLM really is a bunch of coefficients times by the particular variable. So here we're saying they're Q variables. And then what you're going to do is you're going to go in and inspect what these plots of these model coefficients look like. So let's say we're dealing with a categorical variable. You will have a whole bunch of coefficients. So this is the coefficient for the first variable and the first value of that coefficient. And you might decide to go ahead and smooth these. Let's look at what that process looks like on this slide. So here are raw coefficients. You could also derive relativities from these, but let's just call them coefficients from a GLM fit on this data set. And what you can see is that these coefficients there's definitely a relationship, but there's all sorts of noise in these coefficients. So what you might be tempted to do is you might go back to your GLM software and start grouping some of these coefficients. And what I want to point out is that by grouping these coefficients, perhaps changing the value of beta 1 versus beta 2 versus beta 1, if you think about the structure of a GLM, that's exactly the same as smoothing the partial dependence plot of this model or the individual conditional expectation plot of this model. So what I'd like to say and what I'd like to suggest is, in fact, actuaries have always been smoothing PDPs and ICE plots, except we've never actually looked at it that way. So what are some of the ways you can smooth this? This is categorical fusion using a technique called the fused lasso. What you try to get is groups of neighboring coefficients to be similar. Another interesting thing you can do is apply a smoothness constraint. So this is exactly that same set of coefficients where we've both grouped neighboring observations and smoothed, and that looks pretty nice and regular. We've got rid of a lot of the noise. And what you also might think of doing is making sure relationships are monotonic. In this particular case, it doesn't really make much sense, but you can see what forcing monotonicity looks like. And really what we'll be talking about in the ICEnet part of this presentation is how can you enforce those sorts of constraints to ensure that the output from a deep neural network follows the sort of procedure that actuaries have always applied. So let's just talk a little bit about the background here. Smoothness constraints have often been enforced in non-life pricing in a post hoc manner, and this is also true in the life insurance world. So in non-life, you might open up your favorite GLM software and start manually smoothing things out, fitting splines to coefficients, fitting formulas, or grouping them by hand. In the life insurance world, if we've got mainly non-life actuaries, this might be a throwback to your varsity days. In the life insurance world, this is called graduation. And a very popular method for doing that automatically is something called Whittaker-Henderson smoothing, which is exactly what's been applied in this particular plot. It basically makes sure that the rate of change of model outputs is low. Also, monotonicity with respect to covariates is often enforced in actuarial modeling. So in non-life insurance, often you'll do this manually. In life insurance, you find this when you're building up a life table or a set of mortality rates, and you need to close out the mortality table at the end, you will do something that enforces monotonicity. So this is a significant area of judgment when you're building models. What you often find is that in practice, you might only look at the predictive performance of your smoothed model, not of your unsmoothed model, and you might actually realize if you look at the unsmoothed model that there's a huge predictiveness gap as a result of all of the smoothing and other constraints that you impose. That's what you often find is your unconstrained model performs a lot better. And the question that we're trying to answer is how do we enforce these constraints which might be necessary for commercial reasons or for reasons of avoiding poor credibility in your data? How can we enforce this within machine learning models? Gradient boosting machines like XGBoost or LightGBM or whatever you might be thinking of does allow for monotonicity, but the structure of trees in a GBM doesn't allow you to smooth. And I think that's an open problem in GBMs. What the ICEnet is about is a method for imposing smoothness and monotonicity constraints on neural network predictions. A very quick overview of neural nets, just so you understand the diagrams I'm going to show. On the right-hand part of the slide is a diagram using neural net the way this is often presented in the literature. Each circle represents a variable. On the left-hand part of the diagram, you've got input variables. On the right-hand part of the diagram, you've got your output. And because your inputs are directly connected to your outputs using a set of regression coefficients, which are your lines in this particular diagram, what you can see is that this is a way of representing a regression model. You're going to feed a set of covariates in there. You're going to multiply it through by some regression parameters, and you're going to get out a prediction. So this is a way of representing a linear regression or a GLM using the sort of diagrams you have in the neural net literature. What we're actually interested in is a deep neural network. So a deep neural network stacks up a couple of these different layers. You can see here's at the first hidden layer or intermediate layer where there's processing of what you've input into the network. Here's another layer, and then effectively with these sorts of processed and latent variables that the network learns, this is how you're able to make highly accurate predictions using neural net models. And even though the explanation I've given is heuristic, this is pretty close to what happens in practice. So let's now talk about the ICEnet, which is, I guess, what everyone came here for, so let's discuss it eventually. So an ICEnet is a neural network with two main components. The first component of this is a prediction network. So this is exactly as we had on the previous slide. You're going to have a deep neural network where you put in all of your rating factors. It's going to learn a bunch of transformations and then give you a prediction of frequency, severity, pure premium, or whatever else you might be interested in. But then there's also going to be a constraint network. This constraint network, what we're going to do is we're going to feed in exactly the same modified input data that you would use to create an individual conditional expectation plot. So in other words, we're going to vary one of the input variables over the whole range that variable can take. So meaning to say, let's say we want to apply constraints to driver age. We're going to feed in the particular age that we want to predict at. Maybe it's a driver aged 50. But we're also in that same network going to create predictions running all the way from age 18 up to 100. And the network is going to create a prediction on using the prediction component, but it's also going to produce exactly the same outputs as an individual conditional expectation plot. And what we're going to do is constrain this network such that the individual conditional expectation plot is smooth, monotonic, or any other constraint that you can think of. What we'll be focusing on is smoothing and monotonicity. So let's just check that the idea is clear. We're going to have a prediction loss. We're going to try and make sure that the model makes good predictions. We're going to have a way of making sure that the ICE plot is smooth, and also a way of making sure that the ICE plot is monotonic. And now just connecting it to what actuaries have always been doing in non-life rating, which is manually enforcing these sorts of constraints, this is a method of ensuring that happens. So let's just look at a quick diagram. This is your neural network. This is your prediction component, which is going to predict one component. But what we have over here is, at the same time, we're going to have a constraint network. And in the constraint network, we're going to keep varying the value of one of the variables, keeping everything else constant, and then making sure that the predictions from this network are constrained to be smooth, monotonic, or whatever else you'd like. Because this network, both the prediction network and the constraint network, share the same set of parameters, by training this sort of construction, what you're going to get is a network that outputs both smooth and monotonic predictions while maximizing prediction accuracy. So let's maybe just see, is this clear to everyone, what we're doing here? I'm seeing a couple of nods and a lot of non-nods. Can we take some questions now? Sorry, guys, can we get a mic to whoever wants to ask a question here? So maybe let's take 2 questions now, just so we can make sure the main idea is clear, and then we can go from there. Okay. So where do we need a mic? One over here in the front.
Right in the front here, please.
Hello, is it working? Okay. Hi, Ronald. I just wanted to ask, how are you varying the single parameter that you vary? Are you using like a sort of stochastic input, or?
Great question. In this case, it's fully deterministic. So in other words, let's say you've got 80 different integer ages, you just feed that in. So you modify your input data to each one of these components of the constraint network to use, say, that's driver age 18, 19, 20. You could think about doing it stochastically. The problem with smoothing and monotonicity is you always need consecutive penalties. So a stochastic approach will probably just drive everything you've constrained to 0. Okay, I tried that. Good question. Any other quick questions here? Okay, so let's proceed then. Let's look at some examples. So again, this is the French data set. Exactly the same split that we were talking about before. We split this into a 90-10 ratio between training and testing data. And I used a really small network just to keep this nice and simple. 3 layers of hidden neurons, 32, 16, and 8. Neurons, and what's called an embedding layer, which is a really nice way of processing categorical covariates for neural nets. What I've done is choose the value of the constraints as follows. So I really want the driver age to be smooth because if someone has a birthday every year and they don't want their premium to change dramatically. I've also chosen that bonus malus, density, and vehicle power should all be constrained to be monotonic. I've made the choice or applied the actuarial judgment that a more powerful car probably means higher frequency of claims. It doesn't always, but let's go with that over here. And I just really chose these after a little bit of experimentation. We'll see in a little bit how you could choose these in a more automatic way. Fitting this model, both the constraint and the prediction network, takes about 12 minutes on a GPU, would probably take about an hour and a half on a CPU. And what we can see are a couple of the results. FCN is a fully connected network, and nagging in this table is just what happens if you average the predictions over a fully connected network. I think I averaged over 10 or 20. We presented this at the STIC 3 or 4 years ago if you want to go back and see what nagging is all about. And let's look at the out-of-sample data. So we can see that we achieved a Poisson deviance of 0.2383 on the test set without constraints and 0.2385 on the test set with constraints. So in other words, we're going to have hopefully nice, smooth, and monotonic predictions at a very slight loss of predictive accuracy. If you try to fit a GLM to this data set, you're going to get something that is much worse than the ICEnet. So first conclusion is applying constraints doesn't really damage the predictive power of the sort of network. Let's try to decompose the difference in predictive power between applying smoothing constraints on the one hand and monotonicity constraints in the other. So over here, this is the, let's just look at the bottom part of the table. Here's where you have smoothing and monotonicity constraints together. Here's where you only have smoothing, and you can see that in fact, smoothing by itself creates slightly worse performance, but adding a monotonicity constraint actually results in slightly better performance. So the conclusion you can take from there is that at least in this well-used example of a non-life pricing problem, enforcing sensible monotonicity constraints with actuarial judgment can actually improve your pricing models. Smoothing might be necessary for commercial purposes, but might not be that good for the predictive power of your model. Let's have a look at the partial dependence plots. So we've got a whole bunch of partial dependence plots on the right-hand part of the slide. The ones in red are the smoothed ones, and the ones in smooth with smoothness and monotonicity constraints, the ones in blue are the unsmoothed ones. Let's just have a quick look at some of the things I'd like to point out over here. You can see that you've got some absolutely wild predictions that get created for bonus malus. If you've got a client with a frequency of 1, probably your underwriting has failed, as opposed to you shouldn't be pricing for that, in other words. But your constrained networks actually have a much more sensible relationship. So remember, we constrained this to be smooth, and only from the highest scores do you see a bit of a divergence between what's predicted using the ICEnet versus what's predicted using an unconstrained network. Driver age as well, you can see that the partial dependence plots for driver age all follow this sort of function, but over different runs of the neural network, which you might be able to make out over there, you can see that the unconstrained network actually learns a whole bunch of different functional forms for the effect of driver age on your non-life rating. And that in of itself isn't something that you'd necessarily want. You don't want a fundamental relationship in your model to break down or change potentially every time you train it, and that problem also is solved by applying these ICEnet constraints. Let's have a look at whether or not this ICEnet has worked. So what I've done in this next slide is these are a couple of histograms. And let's just walk through what we're showing. We calculated how monotonic your ice plots are with the unconstrained network. That gives you a monotonicity score, and higher means you're less monotonic. And then we recalculated that same score using a network with predictions that had been constrained from your ICEnet. And what these diagrams on the right-hand part of the slide are, this is how does your monotonicity score differ for a sample of a couple thousand policies for bonus malus. And you can see it's got a long left tail. So taking your unconstrained monotonicity score, higher is less monotonic, and subtracting out higher is more monotonic, and subtracting out your constraint actually gives you a long left tail. So that means that in most instances, the differences are either very small, in other words, you already had monotonicity, or you've improved the monotonicity of your model by applying the constraint. Let me just highlight another one, just out of interest. Let's look at smoothness. Smoothness, you can see exactly the same thing. We've got this long left tail, which means that we actually have achieved greater smoothness. In other words, answering the question, the method has worked. Let's just have a look at a couple individual policyholder results. Again, red is with constraints, blue is without constraints, and let's just focus on this particular policyholder. What the unconstrained network predicted is that as your density or the amount of traffic on the roads increases, your frequency of claim actually goes down. So that's a little bit unintuitive. We constrained using this method. On the other hand, that frequency should increase with density, and that's exactly what we see. Another good example is over here on the bottom right-hand part of the slide, where an unconstrained model produces decreasing frequency with vehicle power, but because of our monotonicity constraints, you can see all of these are more or less increasing. So another way of showing that if you don't apply constraints to these types of models, even a relatively simple neural network, you can have all sorts of unpleasant things that come out when you actually get around to rating individual policyholders. I'll just focus on one or two for smoothness. Here's driver age. You can see that we have this very sort of jagged drop and then increase, where that's much more moderate and smooth with the constrained network. So basic bottom line is that applying the ICEnet can give you outputs from your network that if you deployed directly into your rating system would actually be more sensible, keeping the relationships that you want and allowing for adequate smoothing. I'm just going to show you very briefly what I had done in the previous example was select coefficients by hand. What you can also do is a much more machine learning type of approach where you select based on the lowest validation set. Here is where we've applied the same value of the constraint to each run of the model. We've selected the one that produces the best predictive performance on a validation set and now looked at the holdout set. And that best one is illustrated in red over here. You can see, for example, on bonus malus, it's very nice and smooth with a sensible functional form. Smoothing too much gives you something that's basically flat. And you can see a similar effect all the way through, that applying the sorts of constraints we've been talking about gives you outputs that I believe are better for non-life rating. I just want to touch on an extension of this and then we'll conclude the talk. So what someone in the audience asked is, could you do a stochastic version of this? We're not going to show a stochastic version, but we're going to show a local version. And really what the local version of this does is, instead of looking at the whole window of the covariates, just look at a little local window around each value. So let's say we've got a driver age 50 in a particular record, instead of looking at and applying constraints to that entire age range from 18 to 100, you might just want to apply constraints from, say, 48 to 52. And that's exactly what we've done. Interestingly, 2 points to make. One is it's much easier to fit. You don't need a GPU anymore. You can fit it on CPU. Another interesting point is actually only smoothing over a small window means that applying these constraints doesn't damage the predictive performance of your model at all. And this is probably a good practical solution to applying constraints without needing a ton of computing power. What you can see in these plots is, particularly on the smoothing side, things have worked really well. On the monotonicity side, if you remember how to interpret these diagrams, not so much. So the one takeaway over here is you can approximate this idea of constraints, but you just need to be a little bit more careful if things actually work. Let's look at the implication of applying this extension on that same graph. You can see here you've turned density around. That's great. It's moving in the right direction. In this particular one, it's better than a very big, significant decrease in frequency due to vehicle power, but it's not exactly monotonic. In fact, it's monotonically decreasing. So kind of a mixed result, but it will get you part of the way there. And I'm not going to talk too much about this slide because I'm more or less out of time, but you see the same thing on smoothing. So let's conclude and let's see if there's any other questions from the audience. What have we done today? We've walked through a novel approach for constraining neural networks to be monotonic and smooth. We've connected this to the individual conditional expectation model interpretability technique, and also shown both a global version as well as a local version that you can approximate and run a little bit more easily. I guess a couple of points is that what we've seen in fitting these models to a real-world data set is monotonicity constraints can improve the out-of-sample performance of your models, which shouldn't come as too much of a surprise if you think of the fact that some relationships are relatively obvious in non-life rating at least. Models with a combination of fitting of smoothing and monotonicity penalties allows your models to produce predicted frequencies of claim that make sense intuitively and also don't take away too much from the predictive performance of your model. Something else you could try is impose constraints on the global behavior of your model. So in other words, constrain the PDP instead of the ICE. And that's something that is quite interesting and might also lead to good results. And you could also apply other sorts of constraints. So you could, for example, apply the fused-Lassus for a different type of penalty. Maybe some discussion points to trigger some questions in the audience. Do we need smoothness constraints for non-life pricing? So what we've seen is that there's a balance between applying smoothing and getting things that might look reasonable to a policyholder or a broker, but on the other hand, you lose a bit of predictive accuracy. So do we need smoothing? Is perhaps a fusion constraint, like we showed at the beginning of the talk, a better choice for practical rating? Are there any other things we should be thinking about? Maybe constraints for categorical variables like vehicle, make, model, etc. And with those thoughts in mind, let me leave you with the last comment that if this is interesting, please have a look at the paper, and you can find all references to the various things that we've spoken about here at the end of that paper. So thank you for listening, and I look forward to your questions.
Thank you so much, Ronald.
Thank you.
That was insightful and deep. Much appreciated. So we're going to go into questions. For our participants that are joining us virtually, you are most welcome to put your questions in the Q&A function on our app. And for those of you joining us in person, you may just indicate if you have a question by raising your hand. So you can raise your hand and we'll get the microphone to you and you'll ask your question. And as we hopefully get one or two questions or more than that, Ronald, as I was listening to you, I looked around the room and look at all of us as actuaries in here. I'm thinking, we probably have two types of actuaries that listen to you. One type would have heard you speaking and it sounded very English and understandable. The other type would have listened to what you were speaking and thought you are a Greek speaker. And the question I have is, with the world moving towards machine learning models and the adoption of AI, is the understanding and the ability to apply machine learning as actuaries now table stakes? Is it minimum entry? Is it minimum requirements for us?
Yeah, I think it's such a good question. I think the actuarial profession actually has a choice over here. Either we can be the ones applying machine learning for ourselves, or someone else is going to come in and do it for us. And at the end of the day, it's just a question of what do we and what is our vision of the actuarial profession going forward? Should we be the experts in modeling and have the ability through teaching actuarial students correctly, maybe including an exam on this in the syllabus? Is that the route we want to go? Or do we want to start becoming more qualitative and perhaps reviewing models, but not actually being able to build them? And what I sincerely hope the actuarial profession chooses is for people to understand this sort of presentation and not think it's in a foreign language. So I think what actuaries have always brought to the table is a combination of technical excellence together with the ability to communicate that, to make judgments about that, and to get senior stakeholders to understand what we're doing. And I think if we don't make the move to new sets of techniques and technologies that are going to become more and more popular, we'll lose our seat at the table.
Yeah, powerful. Any questions from our audience in person? We have a question right in the middle. Thank you.
While we're getting the microphone through, let me just say to those joining online, we're aware of the fact that there were some technical issues in the first few minutes of the presentation, which meant you didn't see some of the earlier slides. So if there are follow-up questions from what you heard but couldn't see, please feel free to just circle back to those and pop us a question in the app Q&A section. Back to the floor. Good morning.
Morning. Thanks, Ronald. You spoke about some of the machine learning models being black box. You don't exactly know what it does, but it produces results, and they're even more accurate than the linear models that you can explain. Have you ever faced a challenge, practically in the corporate world with this black box issue, or is it something? How do you explain it to people if you are cornered to say, what is your model doing? How do you know what it's doing? Or it's not an issue at all? Thanks.
I think it's such a great question. In the South African environment, the only people you need to explain it to are your actuaries generally and your customers. In other jurisdictions, particularly in the United States, you also need to explain it to your regulator. So in South Africa and the UK, regulators don't really look at pricing models, at least at this point in time. I think implementing a black box model, if you've got actuarial stakeholders who are used to explainability, is going to be very challenging. And I think what we also showed in this particular presentation, that the outputs of the models may not be fit for purpose as they are until you start modifying them to be closer to outputs that we think are commercially sensible. So I think black box models with constraints offers a really interesting way to bridge the two. Because if you can show senior stakeholders, but also have faith that the outputs will be suitable for your customers, I think you're in that position where the black boxness doesn't matter so much. So that would be my answer based on this presentation.
We have a question on the floor.
Can we please have assistance with the microphone at the front?
Okay, there we go. Hi, Ron. Practically, what can we do to test out ICEnet ourselves?
So great question. If you read the paper, you'll see all the code is there. It's in R. Maybe someone in the audience would like to translate it into Python for us. But yeah, you're absolutely welcome to go grab that code, understand it. You're welcome to email me if you want to work through it, and I'm happy to assist. So we've tried to make it quite nice and open, but it's actually not so complex to implement yourself. So if you just think about the core thing that we're doing, you modify the input data and you add some constraints, and that's basically it. So hope that satisfies.
We have a question in the front, if we can get the microphone here.
I just wanted to ask how you optimized your constraints, like the regularization.
So the way that you do this, I see the slides are gone. It all comes down to specifying the right loss function. So the loss function for a neural network is generally something that emphasizes predictive accuracy. And what's really nice is you can use the sorts of things that have always been used in GLMs, like Poisson deviance or gamma deviance for severity. And then you also introduce that idea of a loss function that measures smoothness and monotonicity. And what your deep neural network software does, but also things like custom loss functions and XGBoost, it just does its best to minimize that loss function. So as long as you specified it correctly, it's basically very easy to do. The reason I think it would be quite difficult to implement this in XGBoost or one of the other boosting packages is you do need a multivariate output that you can evaluate those loss functions on. And that's traditionally not been supported in most of the boosting software. There've been some recent efforts to develop multivariate output GBMs. So as long as you can implement, you've got some sort of software package that implements an optimizer, this is really easy.
I think we could take one last question. There's a gentleman who's had his hand up for a while in the middle section there, and I can see that hand is tired. So let us relieve him.
Okay, thank you. Beautiful presentation. But as the gentleman explained, the theory behind this is very complicated. I just want to know, like, the judgment that goes towards the constraints, right? How do we know that what we are imposing on the model is actually correct? Because, for example, the model is telling us that as density increases, then the model goes down. And as power increases, the model goes up. But that could be inherent in the business mix that we have, because maybe people with fast cars actually take care of cars, and when there's higher density, there is more alertness, like in traffic. There could be variables that we are missing and just adding on constraints to make the narrative better.
I think that's a really good question. Let me give two answers. I suppose the one answer is, if you impose a constraint that's really not right for your data, you'll see the predictive performance fall off a cliff. So all of a sudden, you'll be much, much worse than data that hasn't been constrained. Or you'll start to see that the way that the model has fit these ice plots is nonsensical. So you might just see everything becoming flat. And in my experience, that's a really good way of interpreting whether or not you've chosen the right constraint. I really like the example you gave of why increasing density could lead to decreasing frequency, right? So if you really believe that, there's nothing stopping you from implementing a two-dimensional constraint, which is density and I can't remember the other variable you mentioned together. And that will allow you to have a more subtle impact on the model than maybe what we're currently doing. Also, maybe just a third point, remember that you're dealing with a multivariate model, and a lot of these variables are correlated. So even if you impose the wrong constraint on one variable, often you'll have another variable that's close enough, that's unconstrained, to absorb any of the issues that creates. So that's another way of looking at it.
Right, I think we're going to wrap there. Thank you so much for a really, even as one sitting in the Greek camp, fascinating and insightful and exciting presentation. Ronald, RICHMAN, thank you, everybody. And thank you to the floor members for your questions. Just a reminder, if you would like to engage further on this topic, Ronald's paper is available. You can reach out to him via the WebEx app, and of course there is the networking session this afternoon. If you want to hunt him down and pick his brain in person, please do use that opportunity. Katlego, we've got a minute or two before our second session starts.
Yep.
So just to say, if anybody is wanting to skip between presentations, now's your opportunity to do so. We will start in a minute or two with our next session on disruptive technology and innovation. You're welcome, of course, to stay with us for that. Thank you. Thanks to those joining us online, and apologies again for the technical issues at the start. Glad to see everything's running smoothly now.